Math 1314, Tyler Junior College, Section 3.3, Dividing Polynomials, Remainder and Factor Theorems. So as the title of the section implies, there's a lot going on here. But before we just jump into what these things are, I want to motivate what's about to happen. If you watched the last video in the previous series and made it all the way to the end, because it was an unusually long video, you'll notice that you'll recall that I looked at a particular example that created an issue. The example was, let's say we want to find the zeros of this function, f of x equals x to the third power plus 2x to the second power minus 7x plus 4. Now, why would we want to do this? Well, one reason is perhaps we're sketching the graph of this function and we're locating its x-intercepts. Remember, the x-intercepts are the values that make the function equal to 0, which is the definition of the zeros of the function. But the problem with trying to solve this equal to 0 is that we would have to get it factored, and as was demonstrated in the previous video, this will not factor by grouping. You can try it, but it'll fail because when you take the GCF out of each half, the remaining parentheses don't match, a necessary condition for factoring by grouping. However, it will factor if we have a couple of tricks up our sleeve. Trick number one is to observe that 1 is a 0 of this function. In other words, if I substitute 1 into this function, I'll get 1 plus 2 minus 7 plus 4, which is equal to 0. Now, you might be questioning, how can I just observe a 0? I mean, if I'm finding the 0, shouldn't I have to solve? That's true, but let's just work on the assumption right now that we notice that 1 is one of the values that we're looking for. Now, why is this advantageous? Well, recall what happens when you solve a polynomial function equal to 0. You factor it, you set each factor equal to 0, and then you finish solving. Since we know that 1 is the 0 of this function, so in other words, since f of 1 equals 0, then x equals 1 is a solution to f of x equals 0, which is what we're looking for. We're looking for the solutions to that equation, the zeros of that function. And we have one of them, but there would be more. So how can we use this to our advantage? Well, if we were solving this equation, x to the third power plus 2x to the second power minus 7x plus 4 equal to 0, and at the end, one of our solutions was x equals 1, then I know what the preceding step would have been immediately before getting here. Because remember, the strategy is to get this thing factored, set each factor equal to 0, and then solve. Well, if I solved something equal to 0 and got x equals 1, then that equation would have been x minus 1 equals 0. Well, that means x minus 1 was a factor. What's the other factor? I don't know. But because I currently know one of the zeros of the function, I can reconstruct the factor that it came from. This is getting a little ahead of how this section would normally flow, but I want to go ahead and introduce something to you called the factor theorem. Recall that a theorem is a mathematical statement that has been proven to be true. So it's not like we think this works, we know it works and it can be proven. The factor theorem basically says what we just did here. That if we have a 0 of a function, then it comes from a factor and vice versa. So it goes something like this. X equals some number, we'll call it C, is a 0 of f of x if and only if x minus c is a factor of f of x, which kind of makes sense based on the discussion that we've had over here. When you have a factor of a polynomial function, then setting that function equal to 0 means that you would set this factor equal to 0 and then solve it. But we can reverse that process. If we have a 0 of the function, we could just move it back to the left side of the equation, subtracting from the x. Of course, if this 0 were negative, then when we move it, it would look positive here. But now that we have this small equation equal to 0, that means that this small equation, this small binomial, was one of the factors. So zeros and factors go hand in hand. You can't have one without the other. If you have a 0, you have a factor, and if you have a factor, you have a 0. So that's kind of helpful, because if we're attempting to factor a polynomial that doesn't succumb to previous factoring techniques like grouping, then we can find one factor if we know a 0 of the function. But this raises two natural questions. Actually, before I raise those questions, let's kind of summarize what we know about this function based on the fact that 1 was one of its zeros. Since x equals 1 is a 0 of this particular function f of x, then x minus 1 is a factor of f of x. In other words, i.e., which is the abbreviation for a Latin phrase that I don't recall off the top of my head, but it translates loosely into in other words. In other words, our function can be written as x minus 1 times another factor, and since I don't know it, I'll just call it g of x. And the two questions that this raises, number one, if we know x minus 1 is one factor, comma, what is its, and I'm going to coin a new term here, cofactor, which we're currently calling g of x. You can't have one factor without another. A factor is part of a multiplication problem. So there's got to be another part to it. So if we know one factor, how do we get the other? And the other burning question is, given f of x, how can we locate a 0 to begin with? How can we locate a 0 to begin with? It's almost like a circular problem. We're attempting to find zeros by factoring, but we're attempting to factor by first finding a 0. It's a chicken and egg argument. Now the good news is, there's answers to both of these questions. Answers that require no guesswork, but rather just following a procedure. In fact, we can go ahead and answer the first question. If we know one factor, x minus 1, how do we find the other factor? That's like asking you to solve this equation for g of x. Well, I know how to solve for things. I can get this g of x alone if I divide both sides by x minus 1. So in other words, let's get rid of this for a second. In other words, if I know that a function f of x has x minus 1 as one of its factors, but I don't know the other factor, which we're just calling g of x for now. And the question is, what is g of x? That's easy, just divide both sides by x minus 1. That'll cancel this, and so g of x is equal to the original function divided by the factor that we already know. Which raises another question. How do we do this? Well, there's two ways to do it. Long division, which always works, and synthetic division, which sometimes works, but when it works, it's so much more efficient. So this is going to motivate what's going to happen next. In an effort to find the other factor when we know one, we're going to have to figure out how to divide polynomial functions.